Good morning. I have to start the lecture today. So in the last lecture, what we have done, we have introduced the Pauli-Jordan function. And the Pauli-Jordan function is a commutator of two fields, field operators taken at different space-time points. And now I will define two more interesting and important functions, namely the retarded Green's function and the advanced Green's function. So we will look how they are explicitly constructed. And then I will come to the very important notion in quantum field theory, the notion of Feynman propagator. So let us start with the definition of the retarded Green's function. So delta ret is defined in the following way. So it's a function of the difference of two space-time points, x and x prime, and it is given by the product of the Heaviside theta function on t minus t prime, multiplied with a commutator of two fields at different space-time points. So say field at xt and the field at x prime t prime, like this. And you see that if you compare this to the definition of the Pauli-Jordan function, then what is written down here is simply IH bar C theta function t minus t prime multiplied by d on x minus x prime, where this d is a Pauli-Jordan function. Is a Pauli-Jordan function. Okay. Analogously, the advanced Green's function is defined as minus theta t prime minus t, so with a minus sign, and the same commutator phi on xt, phi x prime t prime, like this. So this is minus I h bar c, theta function t prime minus t, multiply with d on x minus x prime. Okay. Of course, we have to show that here the functions introduced in such a way are really Green's functions. In other words, they solve the Klein-Gordon equation with a delta function source on the right-hand side. And this can be done, I mean, this showing that this is indeed the case can be done in different ways. And the simplest way probably to do this is just say to take delta retarded and act on it with the Klein-Gordon propagator. And of course, use then the fact that the field phi on xt solves the Klein-Gordon equation. So let's see how it works. So we take the Klein-Gordon operator, which is essentially c minus 2, so speed of light, derivative, second derivative with respect to time, minus derivatives with respect to special directions, plus mu squared, where mu is, you remember, I'm denoting this mu h bar m as around mc over h bar, mc over h bar. And this we apply to retarded Green function of x minus x prime. So essentially this means that we act with this operator on theta t minus t prime, commutator of phi on xt, phi x prime t prime, like this. And so what we see is that first we apply derivative with respect to time, and applying it, say, once, we will get the following. So minus c squared I will take inside, and the first application of time derivative goes first to theta function. So theta function turns into delta function upon differentiation with respect to the argument t. Then commutator is left, nothing happens to it. And then the time derivative acts on the argument of the field phi. And when it acts on phi, then we know we get phi dot, but phi dot is for a scalar field is nothing else as a canonical momentum. So what we get here then is theta minus t prime, and the commutator of the momentum of the field phi with the field at x prime t prime. Then we have this part of the Klein-Gordon operator, which straightforwardly gets inside the bracket, and acts on the field phi. So these are derivatives with respect to spatial directions. And so what we get here is theta function t minus t prime, commutator, and then minus di squared plus mu squared, acting on phi on xt, and then phi on x prime t prime. Now we have to continue and act with the remaining time derivative on the result inside the brackets. But before doing that, we know the following, that actually because of the delta function here, we would have a non-trivial result only when t is equal to t prime. So we go to the support of the delta function. But in this case, when t is equal to t prime, we have an equal time commutator of two quantum fields phi. And we know that from their canonical commutation relations, for t is equal to t prime, this commutator vanishes. And so, in fact, the whole term here produces a vanishing contribution. We can just drop it. Then we have time derivative, and first it acts on theta function, so it gives us delta t minus t prime multiplied with the commutator pxt pi xt phi on x prime t prime, like this. And then this second application of dt to pi will produce for us, in fact, nothing else as a second derivative of t on a field phi. And this term we can combine with the last one. And so we will get theta t minus t prime. C squared, by the way, must be also, it must be also here. Okay, let's write it like this, minus c squared here. So what we will get is minus c squared dt acting on phi on xt. Or let me probably write it as an operator, as a whole operator acting on the field phi. So I will get here is plus plus c squared dt squared minus di squared plus mu squared all this acting on field phi on xt, and then phi on x prime t prime, like this. So what do we see from this formula? Well, the first thing we see is that since phi on xt is a solution of the Klein-Gordon equation, then this term here vanishes because phi is a solution. So this term disappears and the whole result turns to delta t minus t prime commutator between the momentum of a field and the field itself at different space-time points. And this is something which we can easily compute, because again, due to the delta function here, the argument, time argument t prime can be replaced for t. So what I can do, I can just drop here prime. So this is equal time commutator between the momentum of the field and the field itself. And because of the canonical commutation relation, we know that what is written down here is in fact minus h bar, delta function t minus t prime, delta function x minus x prime. So in other words, we restore here on the right-hand side the four-dimensional delta function minus I h bar c delta four-dimensional delta function delta 4 depending on the difference of x minus x prime, where I made use of x0 equals to x0 equals to ct. Okay, so that shows, in fact, that if I take a Klein-Gordon operator, so let's write it as massive box operator, box plus mu squared, and apply it to the retarded Green's function, x minus x prime, then the result of this is minus I h bar c delta 4 x minus x prime. So indeed, we see that delta ret x minus x prime is a Green's function for the Klein-Gordon operator. Well, quite analogously, well, first of all, maybe you have to answer the question why it's called retarded. It's called retarded because according to its definition, due to the presence of theta function in the definition, you see that this Green's function has a distinguished property that delta ret x minus x prime vanishes for t less than t prime. And Green's function with such a property is called retarded. Quite analogously, you prove the same property. You prove that this equation satisfied, but now for delta advanced. Computation is absolutely the same, and you find that delta advanced is also a fundamental, as people say, fundamental solution of the Klein-Gordon equation. And fundamental means that it's a solution with a right-hand side represented in the form of a point-like source, of an impulse, point-like source. Okay, there is another way to show how the delta retarded is a Green's function, and it also allows you to obtain a useful representation for this Green's function. But before I do that, let me ask if you have some questions. So we continue, and then let us look at the following representation, which in fact uses the integral representation for this Pauli-Jordan function here. So for Pauli-Jordan, we investigated this function, of course, in the previous lecture. So we know what is the integral representation for this function. We obtain it by explicitly substituting the fields in terms of, creation, annihilation operators, computing the commutator, making all these manipulations. So at the end, we got this integral representation. And so using it, delta ret on x, so it's a function actually of one argument. As you see here, it's a function of a difference between x and x prime. So I can write it as a function of one argument x. This I can write as minus h bar c. Again, these constants I'm writing just for completeness, but you can always put them to 1. So h bar and c, if you are in natural units, you can always put them to 1. No problem with this. Let me just mention them for completeness. So integral representation for delta ret goes as follows. So you have theta function because it comes from the definition, but then there is this integral representation, delta k divided by 2 k0, and then there is exponential I omega t minus exponential minus I omega t, and exponential plus I k x. This is integral representation for this function where I have to say what is omega. So k0 is, I'm using either k0 or omega, and so this is component of the wave vector, and this is related to k0 by the following formula. So omega divided by c is k0. And on the other hand, this is the same as square root of k squared plus mu squared. This is what is omega here in an explicit way. Okay, so what I can do with this integral representation, I will start from some auxiliary, or if you wish, additional integral, which apparently at first sight has nothing to do with this delta ret. What I would like to do, I would like just use complex analysis, in particular the residue theorem, to compute the following integral: exponential minus I ck0 multiplied by t dk0. So t is the time. Here is dk0 and k0 plus I epsilon squared. I will tell you what is I epsilon there, minus k squared minus mu squared. So auxiliary integral integral is taken along the real line, but I would like to use the complex analysis. So you should imagine that actually what I'm doing, I'm considering the complex plane of the variable k0, and I'm trying to compute this integral over this integrate over k0 variable all along the real line here, all along the real line. But if I just look at the denominator and forget about this little piece which I'm adding to k0 here, so epsilon is positive and small. Epsilon is positive and small, and I epsilon is therefore a little shift in the imaginary direction. Why I'm doing this? If I forget about this little I epsilon, then my denominator in this formula looks like k0 squared minus k squared minus mu squared. And then you see that when k0 will be running through the whole real line, eventually it will meet here the problem, because at certain values of k0, this expression here may become equal to 0. And this happens when it happens when k0 is equal to plus minus square root of k squared plus mu squared, right? So these are real values, so real numbers. And where do they sit? They sit somewhere here. So one of them is, say, at positive value k squared plus mu squared, and another one is somewhere here at minus k squared plus mu squared. So if I just stay with the original denominator, forgetting about I epsilon term, then I have singularities along the real line. I meet the singularities in the integration contour, and then the integral is not well defined. It will diverge because denominator at these points where denominator vanishes, produce a problem for our integral. And so exactly to overcome this problem and make sense of this integral, what one does, one adds up this a little I epsilon, and adding up this a little I epsilon shifts the pole in the lower half plane by this amount I epsilon. You can see that now poles are shifted from the real line a little bit down. So they are now here. Why it's a little bit down? That's because now you have to solve a different equation. With I epsilon, you can have this equation here. K0 plus I epsilon squared minus k squared minus mu squared is equal to 0. So here you, therefore, when taking the square root, you will get k0 plus I epsilon equals to plus minus square root of k squared plus mu squared. So from here you will conclude that k0 is minus I epsilon plus minus square root of k squared plus mu squared. So indeed, that is where now the poles are. And because of this minus I epsilon, these poles are shifted in the lower half plane. And so this means that now you have no problem if you integrate over the real line. So you go all along this contour. And you can apply the Cauchy theorem to compute this integral by closing the corresponding contour in the lower half plane. So you go through infinity and close the contour in the lower half plane like this. So that's what we will do now. And then we can compute this integral by Cauchy residue theorem in the following way. So we have two poles, this one and this one, and we have to take the residue at these poles. So our integral, which if you allow me to continue here, integral from minus to plus infinity, dk0 divided by, and now I have to compute the residue of this expression, say at the first and the second pole. And by the way, when going around over this half circle, I have to take into account the direction of the integration in the Cauchy theorem. So in the Cauchy theorem, the integration contour should be enclosed in such a way that the region enclosed by this contour must remain on the left. If I will be going in the way I'm doing here, it will be on the right. from the integration contour. So if I go in this direction by continuing moving from left to right over the real line, if I continue, then you see that my integration region will remain to the right from the integration contour. So when integrating, when replacing the integral over the real line by integration over this half circle, I have to change the sign because of changing the way I enclose the contour in order to be in agreement with the Cauchy theorem. So let me then write the answer, and if you will have a questions, I will be ready to answer. So k squared here plus mu squared, and then there is a residue at the first pole, which is exponential minus I c k0 t divided by k0 minus. First of all, what I'm doing here, I'm not yet computing the integral, but I'm decomposing denominator in such a way that it represents now a sum of two simple poles, expressions with two simple poles. This is not yet a computation of the integral. This is just the rewriting of my denominator. I decompose the denominator, in fact, into simple fractions. This is how you should say about this in mathematical terms. So I exhibit these poles in an explicit way. So this is how it looks like, right? So you see, if I now make a common denominator out of these two, I will return back to the original integral. So I've done nothing except here, except exhibiting explicitly this simple pole by decomposing denominator into simple fractions. Now, to compute this integral, you see why I'm enclosing this contour below the real line. That is because for t bigger than 0, you have to look at this exponential minus I c k0 t, and for t positive, you see that k0 should have a negative imaginary part, so it should behave like minus I modulus of k0, roughly speaking. In order for this minus I to be multiplied with this minus I and produce minus in front of the real number, in front of the remaining argument, which is positive, to provide the damping when I go very far away, when I will be taking this contour, the radius of a circle bigger and bigger, this term will provide the corresponding damping required by the application of the Cauchy formula. So for t bigger than 0, I'm enforced actually to close my integral below the real line. In other words, in the lower half k0 plane. And then, of course, I will encounter these two poles, and one pole is at k0 equals to square root of k squared plus mu squared minus I epsilon, as we discussed, and the other pole is at k0 minus k0 k squared plus mu squared, also minus I epsilon. So therefore, by Cauchy's theorem, if you allow me to compute it here, to continue here, I will get 2 pi I divided by 2 square root of k squared plus mu squared. And then the residue in the first pole, what I have to do, I have just to take I C and substitute here the value at the pole, k squared plus mu squared multiplied by t. And in the second one, I will get minus exponential minus IC square root of k squared plus mu squared multiplied by t. And so this is the answer for this auxiliary integral. That is an explicit answer for this auxiliary integral. Now, of course, if you consider t bigger than less than 0, here my argument t can take in the original integral, t can be anything. Can be bigger than 0, and it can be less than 0. For t bigger than 0, we said we need to close the contour in the lower half plane. For t less than 0, the situation is actually the opposite. In order to guarantee the exponential damping of our function at large values of k0, what you have to do, you have to close the contour in the upper half plane. But in the upper half plane, there are no poles. The function has its poles only in the lower half plane. And therefore, here contour is in the upper half plane. But then no zeros there. No poles there, sorry, no poles there. And no poles means that the integral then will be 0. Integral is equal to 0. So what we have then obtained is that we see that this integral has interesting property. For positive t, it gives a non-trivial answer given by this expression here. For negative t, it actually vanishes. It is equal to 0. On the other hand, if you now look at this answer we obtained for t positive, and you return back to this expression here, you see that what I have obtained, what this integral is in fact this quantity here, exactly what stands here. If you plug for omega square root of k squared plus mu squared multiplied by c, then you will see that you get exactly these exponentials, so 2 exponentials. And k0 in the denominator, which is square root of k squared plus mu squared, is exactly this term here. So you see that instead of now this expression which we got, we can just substitute in the original integral representation for the retarded Green's function our auxiliary integral. We just take it as it is and substitute it instead of the whole expression, which we then integrate over vector k and with the remaining exponential ikx. In other words, what we get for this case is the following expression. Delta ret on x becomes h bar c integral d4k. Here now I perform integration not only special directions of k, but also of this k0 variable. So this is combined in the 4-dimensional integration measure, 2 pi 4. And here I will have I divided by k0 plus I epsilon squared minus k squared minus mu squared exponential minus I kx, where this kx is a relativistic scalar product, relativistic covariant, relativistically covariant scalar product, K mu X mu.
Professor?
Yeah.
As you say that time has to be positive. So if we take time to be negative, so the function will be 0.
The function will be 0, and that is exactly as we want, because you see in front of this delta red, in its definition, there is this theta function, which tells you that this right-hand side vanishes because of the explicit presence of this theta function. But now this theta function, in fact, is included. Its property to vanish when t is less than 0 is taken by this integral, auxiliary integral, which we have computed. So this means that this theta function I drop from the original delta red, and instead of that, the theta function, its property, it's taken by this I epsilon, which stands now in the final answer here. So this is I epsilon is very important because it shows that this delta red vanishes when t is less than 0. So position of this little I epsilon, which we added, is now taking care of vanishing of this retarded green function. That's why the name retarded, for negative values of time, for negative values of time.
If we apply the time reversal operator to this field, so will it be 0?
Say it again. So say it.
So if we apply a time reversal operator to this field, so will it be 0? It cannot, time cannot be negative.
Time can be negative, but then delta red vanishes. Delta red vanishes. A retarded Green's function for negative values of time will vanish.
So it means that there is no wave function, scalar field.
It just means the property of this delta red. So once again, you probably know from the courses on mathematical physics that the Green's function is not unique. What I was telling is that the Green's function is not uniquely defined for the following reason. So Green's function is supposed for us, at least, to solve the following equation: box, which is this Klein-Gordon operator plus mu squared, acting on the Green's function, should give us something which is proportional to this delta 4x minus x prime. But it's clear that if you find one particular solution of this equation, then you can always add to this solution solution of the homogeneous equation. And this is, again, will be a Green's function. Solution of the homogeneous equation means that delta plus mu squared g hom is equal to 0. That's a usual statement about Green's functions. So that means that playing with this solution of the homogeneous equation, you can adjust the properties of the Green's function you want to construct in various ways. For instance, you can have retarded solution. For instance, you can have advanced solution. And what is more interesting to us is another type of solution, which is called Feynman Propagator. And retarded means just a specific property that Green's function, how to say, appears to be developed after the appearance, after the acting of the impulse. So if you have a delta function source which switches on at t is equal to t prime, sorry, other way around. Yeah, so this is a source which switches on at t is equal to t prime. then the signal propagates at later times, and that is what retarded Green's function is taken care of. Then there is a retarded, it has a retarded property, which means that at the later of values of time, we expect to get consequences of this signal. We observe them in the fact that d retarded for t bigger than 0 is non-trivial. On the other hand, before the source switched on, this d retarded, say, no, here I have to write bigger t prime and less than t prime. This delta retarded is actually equal to 0. Up to appearance of a source, nothing happened, no propagation of a signal, and that's why this delta retarded is equal to 0. An advanced function has an opposite property.
So no source, no function. You mean to say like this?
Yeah. So wavefront, in a sense, wavefront, it's just like in these classical waves. You have a delta function source, so source worked at a certain moment of time at t is equal to t prime. You switched it on, and then you get a spherical wave propagating from this source. But before, there is nothing. And then the wavefront goes on, and its propagation is described by means of this Green's function. Okay, so that's just like this is what you have from the classical theory, because the Green's function itself, in fact, it's something which is attributed and very well known for wave processes, and here we exactly are solving just a wave equation. Yes, it's a wave equation. No, with this mask term here, we have standard equation of mathematical physics, and according to this, we classify Green's functions as retarded, advanced, and maybe something else, depending on how you choose this homogeneous function. So coming back to this delta retarded, what we got, so we got that this delta retarded on x is h bar c, 4-dimensional integral over k, 2 pi 4, nice 4-dimensional Fourier integral, I and then k0 plus I epsilon squared minus k squared minus mu squared, and then this exponential, sometimes my pen does not want to write, minus mu squared, and then exponential minus ikx. And I told you that this is I epsilon here is important. It's important in particular that it stands exactly in this way as it stands under the square. Now, with this representation, you can also elementary check that Klein-Gordon operator acting on delta retarded produce a delta function. So you have d mu, this is my box. That's the same as box. So box, let's write box. Box plus mu squared acting on delta ret. If you use this integral representation, then what we see here is d mu operator. So this is in covariant ways d mu. So by this d mu, we act on this exponential because only this exponential depends on x, and we have to apply these derivatives with respect to the variable x. And so when we apply these derivatives, so what you see is that you get d4k divided by 2 pi in the power 4 I, and here k is 0 plus I epsilon squared minus k squared minus mu squared. And okay, so let's take this I out of. Yeah.
Why should a wave function should only depend on x? Yeah, okay, I understand. So it's a four component, right? K mu x mu.
Yeah. So this is so it does depend on x from the very beginning. So it's a function of x. X here is for vector. So it has 0 component, which is time component, time. So delta retarded depends on time. And it also depends on spatial directions. And this, in a covariant writing, this operator is d over dx mu, d over dx mu. And so with these derivatives, we have now to act inside the integral on this exponential. And when we do this, we get k squared down, but k squared been written in a covariant, been written explicitly, it's k0 squared relativistic interval, k0 squared minus k squared. Now, and then there is also a mass term here, minus mu squared, and I've taken minus sign, I guess, because I minus I gets down twice, it will produce overall minus, which I'm taking away. And so you see that in the numerator and the denominator and numerator, you have almost the same expression, with only difference that this is little I epsilon. And so then you see that if you take the limit delta ret of this expression minus I h bar c lim epsilon tending to 0 of this integral here, then the result of this will be, and then exponential, of course, is left over here. Then the result of this will be d4k divided by 2 pi in the power 4 with this little prefactor minus I h bar c exponential minus I kx. This is what will be left over. But this is, of course, a Fourier image of the 4-dimensional delta function, delta 4x. And you again come to the same conclusion that Klein-Gordon operator acting on delta retarded produce you the delta function source. So again, even from this computation, you see that this is a Green's function. And again, the fact that it's retarded is now encoded in this position of I epsilon there. Okay, but the most interesting function to us, which is essential element of quantum field theory, is a so-called causal Green's function. Causal Green's function. And this is the same as Feynman propagator. Feynman propagator. Feynman propagator. Propagator. So this I will denote simply by delta. It also depends on x minus x prime. And the motivation for its introduction can be given in the following way. So you might look at the what people call vacuum expectation value of two quantum fields, say field phi on x at a point x and phi on x prime. So this is a 2-point function. 2-point function. 2-point means that it depends on x and it depends on x prime. Now, here phi is a quantum field, so we can write it in terms of creation annihilation operators. And then we put this product of phi on x and phi on x prime in between two vacuum states. So often this is called vacuum expectation value for the product of two operators. Vacuum expectation of the product of two operators. Okay, this is something which you can compute in the following way. You know that this is phi 0, and then you can split the fields into positive and negative frequency paths. So for phi on x, you need phi minus x, and for phi on x prime, you take phi plus on x prime. And this is because phi minus on x prime, its contribution acting on the vacuum will produce zero, because this path depends on the annihilation operators, and the annihilation operators annihilate vacuum. And analogously here, if you take phi plus on x, that this path depends on the creation operator, and acting on the left vacuum, it will produce zero. So you will be left over with the phi minus and phi plus, and then you can continue and rewrite it also in the form of the commutator of phi minus on x and phi plus on x prime, like this. That's because, again, if you open this commutator, so the first term will be phi minus phi plus, like I'm writing here. And in the second term of the commutator, you will get minus phi plus phi minus. But again, phi minus acting on the right vacuum will produce zero, and phi plus acting on the left vacuum produce zero. So this term will not contribute, and therefore you can replace the product of fields by the commutator. But then what is written down here is nothing else is as I h bar c, the negative frequency part of the Pauli-Jordan function, depending on x minus x prime. So in other words, this product of fields in the vacuum is I h bar c d minus x minus x prime. Of course, you can compute it from the very beginning by just plugging fields in terms of creation and annihilation operators, again, making all these manipulations with evaluation of integrals and so on. So at the end, you end up exactly with this expression here, which I here computed in a fast way because we know what Pauli-Jordan function is. So negative frequency part of the Pauli-Jordan function. Now, on the other hand, if you think physically about what is written down on the left-hand side, you can say that what is written down here is an amplitude. You can consider this as an amplitude. For the process when at point x prime, at the moment t prime, say t prime less than t, you create, you say, no, here you might think that you are destroying a particle, say, at x prime, and creating a new particle at x. So destroying a particle at x prime and creating a new particle at x.
Excuse me.
Yeah.
Yeah, Professor, is also there, so I'm asking that if is there also an approach of path integral approach here if we try to calculate this?
Yes, we can do this by means of path integral approach. Yes, indeed. So what is exactly your question about the path integral? Sure, we can do this.
Okay.
And this something which we will do in the second part of the course when we come to the discussion of the advanced topics. So let's say it again very clearly once again. So again, if you look at this, what we have done here, we have split the field into creation part and annihilation part. So phi plus here is the creation part. So we can say that the point t, say, we have to agree what is bigger, t or t prime. So let's take t bigger than t prime. So then we can say that the point x prime, what we have done with this phi plus here, we are creating a particle, and then at a later time t, we destroy it. We are destroying a particle. Destroying with the help of this operator phi minus. So let's say there are two space-time points. One is here, say, another is here. Let it be point x here, and let it be point x prime here. And let here t is bigger than t prime. Then we say that here we destroy at x prime. Let's see how I write it. At x prime, we say create. We say we create, and then we destroy. But we can look at this process in a bit different way. So we can say that similar amplitude may be considered when actually we do in an opposite way. We first create a particle at x, but then we destroy it at x prime. So other way around. In fact, in quantum field theory, if you have 2 points x and x prime, you might think that, say, first you get an act of creation, and then later you get an act of destruction. But since these points x and x prime is sort of on equal footing, you can kind of reverse the process, and you can say that you first actually create a particle and then you destroy it. And in order to kind of combine these two processes in one go, one introduces the notion of the Feynman propagator. So delta, it's denoted, as I said, delta x minus x prime. So delta x minus x prime, which is constructed in the following way. So first, I encode the same process as I already explained by means of taking this 2-point function, 2-point product of x and x prime between the vacuum states, and you supply it with a theta function. And theta function prescribes the way how creation annihilation happens in time. So first you say create a particle in t prime, and then particle is destroyed at a later time t. And theta function takes care of this process. But to this, you add up a theta function with an opposite argument, so t prime minus t, and you change the role of creation, and simultaneously you change the role of creation and annihilation with respect to the points x and x prime. So you write it in this way, which now tells you that at an earlier time t, you create a particle at x. Here you will destroy it at x, and here you will create it at x. And now you destroy it at a later time t prime, which according to the theta function happens later. And so this object here, delta on x and x, is exactly what is called Feynman propagator. If you think about it, what is written down here, you can encode these two terms into one formula. Namely, you can write this as vacuum expectation value of what is called t-ordered product of fields. T phi on x, phi on x prime. Where this operation of t ordering explicitly means exactly what I have written down here. And in terms of words, if you want to formulate this operation by saying words, by expressing it in words, then it means that this t checks the time dependence, time arguments of these fields phi and phi prime. And then it puts these two fields in order. So it orders them according to the time dependence of these fields. The field with a less value of t always go to the right. Always go to the right. Always puts on a right position to the field which has a bigger argument of time. So if you wish, you can very easily remember this rule, this t-ordered rule, by slogan that use is always right. So the younger you are, the righter you are. The younger operator is, the more to the right it stands. You remember, we had already this notion of normal ordered product of fields, and now this is a new notion which is called of t-ordered product. T-ordered product. So you see it here. So this first theta function makes sure that this term here, the first term, is non-zero. It provides a non-vanishing contribution when t is bigger than t prime. And so operator which has value t prime is in fact younger. And that's why it stands righter from the operator phi on x, for which the argument t has bigger value. And then there is a second term here. It takes care of the opposite situation. So it may happen that their t prime value is bigger than t. So t operator with t is younger, and then this operator which is younger stands to the right from the operator with a higher value of t. So that's exactly in these two terms we implement this t-ordered product rule. And if you wish, you can just continue with expressing this Feynman propagator in terms of Pauli-Jordan function. In fact, we have done already here half of the job. So we just need to say that we supply these Pauli-Jordan functions with theta functions. So in the first case, I have theta t minus t prime d minus function of x minus x prime. And to this, I have to add up theta function of t prime minus t in an opposite situation, d minus on an opposite x prime minus x, because now fields are put in a different order. And the Pauli-Jordan function, it's positive and negative frequency part. They also have a property that d plus on x is equal to minus d minus on x. If you look explicitly at positive and negative frequency part, then this is a property. And so if you wish of minus x, sorry, of minus x. And so if you wish, you can here write this d minus in terms of minus d plus. Then this will become minus theta t prime minus t, d plus on the same argument x minus x prime. If you wish, you can do this substitution there.
Okay,
and
sir.
again, yeah.
Sorry to interrupt. Am I right that the scalar field is its own antiparticle, right?
It depends. If it's a real scalar field, then this is the case. If it's a real scalar field, then this is the case.
So this is for the real scalar field, right?
This is the real scalar field which we are discussing now. Yes, indeed.
So so physically we can say that because for 2 points we cannot distinguish a particle for that it's traveling from point A to point B, or it's or point B to point A. So that's why we are superposing the 2 times here, t minus t prime and then t prime minus t.
Yes, but this definition is general. It applies not only to a scalar field, it applies to any to any field of the quantum field theory. So later on, we consider the propagator for the Dirac field, for electromagnetic field. It's a general definition. I'm just demonstrating it here in an explicit way for the case of a scalar field. But the definition is general. You take time-ordered product of the two-point function of this field, vacuum expectation value of time-ordered product of two fields. That's a general definition of what is called Feynman propagator.
So if it's like a spin 1, spin 2 also, like means higher spin, so there also will use this means superposition of time.
Yes, absolutely. This is in a way ordering of fields with respect to the time argument. Ordering of fields with respect to the time argument. So you take, say, for instance, spinor field, or you take electromagnetic field, you take product of the corresponding operators, say, of electromagnetic field, and you order them with the help of this operation of time ordering, and then you compute this vacuum expectation. That gives you a number. This gives you function depending on this x and x prime. And this function is Feynman propagator.
Okay.
Actually, it was originally, I think the first person who introduced this Feynman propagator was Stuckelberg. And this was around 1942. And later on, 1948, I think it was just introduced for some purposes, but in a way, I mean, the fame for this propagator came through the work of Feynman, of course. And I think this is the reason why this propagator is called Feynman propagator. Feynman propagator. It plays a primary role in the quantum field theory precisely due to the fact that we are talking about, well, you will see it. It's actually the standard way to define what is called in quantum field theory correlation functions. Correlation functions, which actually altogether, this entity of correlation functions is a quantum field theory, in fact, is what you can call a quantum field theory. Anyway, let us consider this Feynman propagator in more detail, and it is useful to repeat the same exercise as we did for the retarded green function. So we take again the same thing, the expression for d minus, integral expression for d minus. This is, as we said, dk divided by 2k0. And I was using an expression before for d minus. Now for what was that? For retarded Green's function, I use just the whole d. Now I take the part of it which is d minus. So minus I ck0t plus I kx. So this is the negative frequency part, integral representation for the negative frequency part of d minus. And if you now put it in the Feynman propagator, so here and here, then what you will get is the following expression. H bar c, again, this is not so important, dk over 2 pi cube, then exponential ikx, and then it will be multiplied with the following combination, theta function on t.
I'm saying that it's a d3k, right? Integration.
D3k, yes, it's D3k here. Indeed, it's D3k. So it's a three-dimensional Fourier integral, if you wish. And then, well, time is here as an additional variable over which we do not integrate. Time is time. Then we have theta on t divided by 2k0 exponential minus I c k0. Actually, k0 I should write to be completely accurate. I write it with a lower subscript. So with subscript t here, plus, and this is a theta function which takes care of the second term in the propagator with opposite value of time, with negative value of time, exponential I c k0t, where this k0 is, as before, square root of k squared plus mu squared. Okay, so this is how this Feynman propagator looks like. And again, we will do the same trick as before. We will trade all this term here, where new integral, one more integral, taken again along the real line in the complex k0 plane, So this means that again, I introduce an auxiliary integral, but it will be different from what I have done, say, for Itadot's Green's function, ck0t, divided by k squared minus mu squared. So this k is four-dimensional k squared, so it's k0 squared minus k squared. And here I put I epsilon in a different way in comparison to what I have done before. Before I put I epsilon close to k0, and then I've taken squared minus k squared minus mu squared. You remember this. This is what I have done before. Now I do it in a different way. I put it just like this here, plus I epsilon. So in other words, what is written down here, if you wish, is dk0 exponential minus I c k0t divided by k0 squared minus k squared minus mu squared plus I epsilon. Again, you can go on and look where the poles are. So again, I'm shifting the poles away from the real line to make my integral well-defined. I shift them a little bit away from the real line, but now these poles are shifted in a different way. How are they shifted? They are shifted in the following. So if I look at the k0 plane again, then you will see that here, again, on the real line, I have these two values, k squared plus mu squared, and k squared plus mu squared with a minus in front. So what I'm doing, I'm shifting the poles like this. Let me write it up here. K squared plus mu squared. I'm shifting the left pole a little bit up and the right pole a little bit down, like this. This is the way how my poles will be now shifted. Again, I'm integrating over the real line, so I can pass between the poles like this along the real line. Now, what is the purpose of such a different shift? This purpose of this shift is to actually, with this integral, to realize the properties of this theta function. So one function should be equal to 1 when t is positive, and another should be equal to 1 when t is negative. This is exactly what is accounted by now adding up I epsilon in the way I did it. So in the first case, we have to consider, just like we did before, the situation where we choose t bigger than 0. So for this case, the contour, the integration contour, again, if you look at this exponential here, it's just like before. We have to close our contour in the lower half plane, just as we did before. And the difference is now we have just only one pole in this integration contour, and so we will find the non-trivial contribution in this case. So if you now say look at this integral, dk0 exponential minus I ck0 t divided by k squared minus mu squared plus I epsilon, then I again split denominator into simple poles and the expression with simple poles. So again, I will not have enough space here, but I will write, and it's here. So you will get exponential minus I ck0 t divided by k0 minus square root of k squared plus mu squared plus I epsilon minus exponential minus I ck0 t divided by k0 plus square root minus I epsilon, like this. So in fact, my splitting into these poles is based on the following way I'm treating k0. So if you find k0, pole condition for k0, you see that this should be written in the following way. So it's a plus minus square root of k squared plus mu squared, and under the square root there is this minus I epsilon, right? Look at this denominator here. Look at this denominator. So the pole condition, I have now to take square root to get k0, and then I epsilon will be under the square root this time, right? But epsilon is small, and so this I can write for small epsilon as plus minus square root of k squared plus mu squared minus plus I epsilon. For epsilon tending to 0, this is the leading term in the expansion. And then this plus minus epsilon, which appear in the representation of this expression, where poles. Now my statement is that for t bigger than 0, then I have to close the contour in the lower half plane and take into account the contribution from the pole in the lower half plane, this one, and this is what corresponds to t bigger than 0, while the other term here will contribute in an opposite situation, where you have to consider the situation t less than 0, and for that you need to close the contour in the upper half plane. So for t bigger, for t less than 0, you have to close the contour in the upper half plane. And before, you remember, for the retarded Green function, the result was 0 because there was no pole in the upper half plane. But now we do have a pole in the upper half plane, this one. And therefore, there will be a non-trivial contribution from it. And so this means that now I can evaluate this integral by using the Cauchy residue theorem, 2 pi I divided by 2 divided by the square root of k squared plus mu squared, k squared plus mu squared. Then the contribution of the first term here will happen when t will be positive, and then the first term contributes as minus exponential minus IC square root of k squared plus mu squared multiplied by t, and minus sign, again, this is because the enclosed region containing the pole remains on the right from the way I'm enclosing the contour. By Cauchy's theorem, it must be on the left. That's why there is this minus sign in front. And then the second term for t less than 0 will produce its contribution as minus theta function minus t, which exactly takes this situation that t is less than 0. And again, evaluation of the residue will give exponential IC square root of k squared plus mu squared multiplied by t. Also, this is an expression we get. And again, just comparing this, what we have for this integral representation of delta coming from d minus, we see that we exactly reproduce these two terms. And so we can now use this fact to write down for delta on x, for Feynman propagator, the representation in terms of the fourfold integral d for k. I'm just replacing this expression with thetas via one-dimensional integral, so my integration becomes integration with a four-dimensional measure, d for k, divided by 2 pi 4 I divided by k squared minus mu squared plus I epsilon exponential minus I kx. And so this is a fundamental formula which shows you a concise and fundamental formula which shows you what the Feynman propagator is. It's what is called causal properties are now encoded exactly in this little shift by I epsilon in the denominator. And from here, you also see that the propagator in the Fourier space, delta on k, I may put tilde here to symbolize that this is a Fourier image, but let's not do that. Let's just write delta on k. Then you see that from this formula, delta on k in the Fourier space, taking inverse Fourier transform, will be simply I divided by k squared minus mu squared plus I epsilon. And today I explain you where this I epsilon comes from. It comes from precisely encoding this causality acts of creation and annihilation particles with the help of this T ordering product. And so T ordering sits in this I epsilon shift in the denominator of the Feynman propagator. What you can do also, you can actually compute this integral explicitly and see how delta on x looks like in the x space in terms of known special functions. So the expression is rather complicated, but you can make the corresponding computation. Actually, I do it in the lecture notes. So if you're interested, please look in there. There I prove that the explicit form of delta on x in the x space is given by h bar c divided by 4 pi squared mc divided by h bar squared with all the constants. I'm writing it with all the constants. K1, so McDonald function or Bessel, which is a particular type of a Bessel function, so it's called McDonald function K1, on the argument mc over h bar. And this causality prescription with I epsilon goes now in the x space as minus x squared plus I epsilon divided by mc over h bar square root of minus x squared plus I epsilon. Plus I epsilon, where x squared is a standard for interval. So x squared is relativistic interval x0 squared minus x squared. So this is how Feynman propagator looks in the X space. And as I said, the passage from here to here is explained. It's a technical thing. It requires quite a computation and understanding. It's rather similar to what we have done actually for the case of Pauli-Jordan function, but I am sure you can do it now yourself with the lecture notes. You can understand how you can pass from this expression to here. Okay, now, the last thing I wanted to discuss with you concerning the scalar field before we go to the case of Dirac field is what is called Yukawa Force. Yukawa Force. So the next issue is Yukawa Force. Before, let me ask if you have some questions concerning this Feynman propagator. This is very important formula which you have to somehow realize and remember, including this origin of this I epsilon shift.
Yeah, I have a question. So the propagator is a causal propagator, but then I think it's not very clear to me why it is causal in physics.
Nor that's in fact the causality is important. Causality is in fact implementation of two things. It's an implementation of the fact that we are in the Minkowski space. So we have Lorentz symmetry, Lorentz transformations. As you see, by the way, this delta, this Feynman propagator, appears not to be an arbitrary function of a space-time point, but it appears to be a relativistic invariant function. You see, it depends on x squared, not on just x and x prime, but it depends in an arbitrary way, but it depends on the relativistic invariant, x squared. So this formula is relativistic invariant. The second thing is that causality encodes also the fact that there are no signals which propagate faster than the speed of light. So field, you need a field to mediate interactions between, say, sources of the field. So you need a mediator which would mediate interaction. And that means that signal cannot propagate with infinite speed from point to point. Just like you assume in mechanics, in the usual mechanics, where you say that positions of all the particles at a given moment of time and the velocities of all particles at a given moment of time immediately defines for you the position and the velocity through, say, Newton's equations of particles of interest. Yeah, so here in quantum field theory, we have to be careful about causal processes. So first there should be the reason, and then there should be a consequence. And between the reason and the consequence, you have to wait for a signal to propagate. And sometimes there are things, there are observables which are causally disconnected because they happen in the regions which are not in causal contact with each other, meaning that, for instance, they are separated by the space-like interval. And somehow your quantum field theory knows about this. It should know about this. And this knowledge should be then somehow encoded into the objects which you would like to study, investigate, and through which you would like to express the properties of the quantum field theory. And these quantities in particular are correlation functions. And the Feynman propagator is the simplest example of the correlation function. In this case, it's a two-point correlation function of their scalar field. So finiteness of the speed of light, finiteness of the signal of propagation is something important. And this is something which leads to this causal phenomena we have to take into account in quantum field theory.
Okay.
Yeah, that's what concerns, so to speak, brief answer to this question. Of course, this question you are asking is very deep. It has many sort of facets of explanation. You can go deeper in comparison to what I just said. But in fact, you can read about this in the books. There is a lot of discussion of causality in quantum field theory and causal effects and how you should understand this. In particular, among the books I recommended you to read, there is one book about conceptual problems in quantum field theory, and I think causality is discussed there at a certain extent. So you may look in also in the discussions there. But the brief answer is the one which I gave to you.
Okay, thank you.
Professor?
So what I would like to do now, I want to actually consider the action for a scalar field in the presence of a linear source.
Professor?
Yeah?
Yeah, as I said, the causality I think is also conserved from that, as you said, that delta of minus t equal to 0. So it will travel only for plus t. So no source means no wave function.
Yeah. Okay.
We can say like that, right?
Yeah.
Yes.
So coming back to the Yukawa Force, I don't think I have much time to say to start this. This is actually a short discussion, it's not so long, but I will do it next time. I'll just tell you that this is about action for a scalar field. So the starting point is an action for a scalar field, which we know. So 1/2 d mu phi minus mu squared over 2 phi squared, so standard action. But we also consider the action for this field in the presence of a source term, j on x, interacting with our field phi on x. So this j on x here is called source term. This source term can be considered as a source for a field phi, and simultaneously what it does, it changes the Hamiltonian of the field phi itself. So in other words, the Hamiltonian and the energy receives an extra contribution from interaction of the field phi with this source, The source here is supposed to be in a way external. So like someone comes to you and represents an extra disturbance, which is described by this function j on x. And this disturbance interacts with the field phi on x, and this interaction term which describes interaction of your disturbance with the field is this linear in j and linear in phi term here. And what we would like to study, you would like to study the response of the field phi on the presence of this source j. So in fact, what I'm having here is a part of the theory which is called linear response theory. What is important for me is that in the presence of this source, the Hamiltonian H receives an extra contribution, which I denote by AJ, and this is given simply by minus integral dx j on x with phi on x. This is an extra contribution, to the energy of field phi on x. Now you understand why it comes with a minus sign, because if I will be deriving the Hamiltonian from this action, I have to do I have to apply the canonical procedure, where the Hamiltonian is given by, say, momentum multiplied by the field, so p phi minus Lagrangian. And so when taking the minus Lagrangian, then this term here comes with a minus sign, and this will produce an extra contribution to the Hamiltonian of my field. And so also in the presence of the source, on the other hand, the equations of motion for my field will be changed. Now it will not be just a Klein-Gordon equation, but it will be Klein-Gordon equation, inhomogeneous Klein-Gordon equation, where on the right-hand side you will have a source term, right? Source. Well, you can easily see by deriving the equation of motion by the procedure of varying the action. So when you will be varying the action to find equations of motion, you will vary this field phi, and so you will get a contribution from this source term. So now this is a way how the equation of motion for field phi will look like in the presence of source. And then we make use of the knowledge of the Green's function. So Green's function becomes important because we know that if we have such an inhomogeneous equation, we can always solve it by using the method of Green's functions, and right solution is phi I divided by h bar c, four-dimensional integral of the Green's function, of a Green's function. We don't know which one to take for the moment. We can take any to write such a solution. Indeed, if you apply now the Klein-Gordon operator to the field phi on x, then this Klein-Gordon operator hits the Green's function under the integral. So this is my mu squared. Hits this g on x minus y, j on y. When it hits, it produces by definition of Green's function minus I h bar c, four-dimensional delta function x minus y. And then we integrate over y. And when integrating over y, this cancel, minus I with minus cancel, we will get just j on x. And so indeed, this is a solution of the equation with a non-trivial source on the right-hand side. So you give me a Green's function, and I write you a solution of the inhomogeneous Klein-Gordon equation. Good. I think for today that is probably all, and so we continue a little bit with the Yukawa force. I will explain the concept of the Yukawa force. It will not take much time, and then we straightforwardly go to the study of the Dirac field, Spinors and Dirac field.